Close your eyes for a moment. Imagine the sound, not wind, but something older than wind. A wall of pressure moving across open ocean at 60 miles per hour, carrying ice in its breath, darkness in its weight. This is a North Atlantic winter storm. And for the people who called this coastline home over 1,000 years ago, this was not a disaster. This was just Tuesday. The Vikings did not flee from these storms. They did not hide underground or pray for the season to pass. They built directly into the path of the storm, and their homes stood for centuries. Some archaeological sites across Norway, Iceland, and Greenland revealed timber frameworks that endured for 200 to 300 years or more, without a single iron nail, without one drop of cement, without any of the materials we consider essential today. But here is the question that no one asks, and it is the only question that matters. How? Not just the technique, not just the timber joints or the stone foundations. The real question is, what did these people understand about nature that we have forgotten? That answer will change the way you see buildings, survival, and maybe even the way you face the hardest moments of your own life. Stay until the end, because the secret is not where you expect it to be. Before we go any further, forget everything you think you know about Viking homes. The image most people carry is a low, dark, smoky hut, mud floors, animals living alongside people, a primitive shelter barely holding against the cold. That image is not just incomplete, it is almost entirely wrong. What archaeologists have uncovered, particularly at sites like Borg in Lofoten, Norway, where excavations revealed a longhouse stretching nearly 83 meters in length, tells a profoundly different story. These were not huts, they were living fortresses. The longhouse, langhus in Old Norse, was the center of the Viking world. A single structure served as home, great hall, storage warehouse, livestock shelter, and workshop simultaneously. Entire clans lived, worked, decided, and mourned within the same walls. Dozens of people, one roof, one fire, one shared heartbeat. The scale of these buildings was not accidental. It was engineered, deliberately, precisely, with a level of structural thinking that modern architects still study with genuine respect. And the storm outside? It was not the enemy these builders feared most. The real enemy was something quieter, something that worked in the dark, while everyone slept. Water. Not the dramatic, crashing waves of a storm surge. Not the visible flood that sweeps through a valley. The enemy that destroyed most wooden structures in Scandinavia was quiet, patient, and invisible. Ground moisture seeping upward through soil, rain pooling at the base of walls, snowmelt finding every crack that wood offers when it sits directly on earth. A wooden post driven into damp Scandinavian ground will begin to rot within 5 to 7 years. In a century, it becomes dust. The Vikings understood this with absolute clarity, not from textbooks, but from watching their fathers' houses slowly disappear into the soil. So their first act of genius had nothing to do with walls or roofs. It was about lifting the house off the ground entirely. They built what we now call a dry stone foundation. Flat boulders, carefully selected, fitted together without mortar, without binding agent of any kind. No cement, no clay. Just stone reading stone, each boulder chosen for how precisely it could bear the weight and distributed evenly across the surface beneath. These foundation stones served 3 functions simultaneously. They raised the critical base beam, called the sillstock or lager, above the wet earth, keeping it permanently dry. They allowed air to circulate freely beneath the structure, carrying moisture away before it could settle. And they created a thermal barrier, preventing the frozen ground of winter from conducting cold directly into the floor above. Archaeological evidence from multiple Norse sites suggests these stone foundations required extraordinary precision. Some fitted stone walls show gaps of less than 2 centimeters across their entire length, achieved using only hand tools and generational knowledge passed from builder to builder. The house did not begin with walls. It began with the decision to never touch the ground. But a dry foundation only solves half the problem, because what happens when the storm finally arrives, and the walls must answer? Here is something that might reframe everything you thought you understood about Viking craftsmanship. The same hands that built the Longhouse also built the Drakkar. The same mind that designed a hull to flex across open ocean also designed a wall to breathe against hurricane-force winds. This was not coincidence. This was the same philosophy, applied to two different problems. The technique is called stav construction, post and beam building, and its logic is almost counterintuitive. Instead of stacking horizontal logs, the method most cultures used, Viking builders stood massive vertical posts at key structural points. Into these posts, craftsmen carved deep vertical grooves with remarkable precision. Then horizontal planks, called tilja, were slid into those grooves, one board above another, from floor to ceiling, without a single fastener holding them in place. They sat there, loose, deliberately loose, because wood is not a dead material. A living tree breathes, expands in humidity, contracts in heat. A rigid wall fights that movement, and eventually, the wood wins, splitting the joints, opening gaps, breaking connections. But a Viking wall allowed the movement. The boards could shift slightly within their grooves, absorbing the lateral pressure of wind gusts, the way a ship's hull absorbs the lateral pressure of waves. When a North Atlantic storm struck these walls, the structure did not resist until something broke. It received the force, distributed it across every plank, and released it, the way water moves around a stone, rather than shattering against it. This was not primitive building. This was biomechanical engineering, developed centuries before that phrase existed. Experimental reconstructions at sites including Stiklestad, Norway, suggest these flexible wall systems could withstand lateral wind loads that would structurally compromise equivalent modern timber frame constructions. The ship never left land. It simply learned to stand still. But if these walls could flex and breathe, what was actually holding up the roof? The answer will genuinely surprise you. Stop for a moment and think about what you just learned. The walls of a Viking longhouse were designed to move, to flex, to breathe with the storm rather than fight it, which means they were never rigid enough to bear the weight of what sat above them. Tons of timber, earth and snow pressing down from a roof that could accumulate 2 to 3 meters of packed snow in a single Norwegian winter. So if the walls don't hold up the roof, what does? The answer was hidden in plain sight, running the entire length of the hall like a second spine inside the body of the building. 2 rows of massive interior posts, carved from the trunks of old-growth trees, some estimated to have been 40 to 60 centimeters in diameter, were set into the ground along the central axis of the longhouse. These posts stood independent of the outer walls entirely. They were their own structure, their own skeleton, bearing every gram of the roof's enormous weight directly into the earth below. At the top of these posts, heavy crossbeams connected each pair across the width of the hall. And above those crossbeams ran the single most important timber in the entire building, the ridge beam, a continuous spine of wood stretching the full length of the structure, upon which every rafter rested. This inner skeleton and the outer shell were 2 completely separate systems performing 2 completely different functions. The interior frame carried the weight. The exterior walls stopped the wind. This division of labor was not accidental. It was a deliberate engineering philosophy, and it produced something that went far beyond structural efficiency. Because when the outer walls carry no load, they can be built lighter, modified more easily, even partially removed and replaced without touching the load-bearing frame. Archaeological evidence from the Borg Longhouse excavation in Lofoten, currently the largest Viking Age building ever discovered in Scandinavia, shows clear post-hole patterns consistent with this dual-structure system, with interior post positions maintained consistently across multiple rebuild phases spanning generations. The house was rebuilt around its own skeleton. The skeleton never moved, but even the most perfectly engineered skeleton is only as strong as the connections holding it together. And this is where Viking builders did something so elegant, so quietly brilliant, that modern timber engineers still reference it today. They built a nail that got stronger every time it rained. Iron was precious in the Viking world, not scarce. The Norse had access to bog iron across Scandinavia, but expensive in terms of the labor required to smelt, work, and shape it. Iron went to swords. Iron went to axe heads. Iron went to the rivets of ships that needed to flex at sea without splitting apart. For houses, Viking builders used something that cost nothing and outperformed iron in almost every measurable way. They used wood to fasten wood. The tree nail, a wooden peg, Typically cut from oak, ash, or juniper, woods chosen specifically for their density and hardness was the primary fastening technology of Norse construction. But calling it simply a peg fundamentally misrepresents what it was. This was a precision instrument, engineered to exploit the physical properties of timber in a way that a metal nail fundamentally cannot. The process began with selection. The wood chosen for tree nails had to be harder and denser than the structural timbers it would join. It was then shaped, not into a simple cylinder, but often into an octagonal or square cross-section, so that when driven into a drilled hole, its edges would bite into the surrounding wood fiber, creating immediate mechanical resistance. Then came the critical step. The finished tree nail was dried aggressively, held near fire, left in direct sun, until every trace of moisture had been drawn out. It became lighter, harder, slightly smaller in diameter than the hole it would enter. It was driven through both timbers, wedged at both ends with small wooden splits for initial fixation, and then it waited, because the surrounding structure, exposed to Scandinavian air, to rain, to the slow breath of seasons, was always more humid than the over-dried peg inside it. Moisture moved inward. The tree nail began to swell. Slowly, invisibly, with force that cannot be rushed and cannot be reversed, it expanded inside the hole until it filled every microscopic void in the surrounding wood fiber. The joint did not just hold. It became one continuous piece of timber. Compare this to an iron nail driven into the same joint. Iron corrodes, rust expands, fracturing the wood fiber around it. The very process of oxidation that weakens the metal also destroys the material it was meant to hold. Within decades, an iron-fastened joint in a humid climate begins to fail from the inside. The tree nail got stronger with every rainfall. The iron nail got weaker. In a climate defined by moisture, where rain falls more than 200 days per year across much of coastal Norway, this was not a minor advantage. It was the difference between a building that lasted decades and one that lasted centuries. But fastening timber together was only half of the craft. The other half was knowing exactly how to cut the wood before the tree nail ever entered the picture, and this knowledge was passed down like a secret language that very few people outside the Norse world ever learned to read. Every culture that has ever built in timber developed some version of the mortise and tenon joint. The Egyptians used it, the Chinese refined it, the Romans exported it across their empire. But the Norse version was different, not in its basic form, but in what it understood about failure. Most ancient builders used the mortise and tenon to create rigidity, lock the joint, prevent all movement, build something immovable. The Viking carpenter used the same joint to do the opposite, to create controlled movement within a fixed connection, a joint that could absorb stress without transferring it destructively to the surrounding structure. The basic form is familiar, a projecting tenon, carved from the end of one timber with axe and chisel, to tolerances that modern researchers estimate at 2 to 3 millimeters, fits precisely into a mortise, a socket cut into the receiving timber. The fit was never forced. It was never sloppy. It was exact, because an exact fit meant the load transferred through wood fiber rather than through the fastener, and wood fiber under compression is extraordinarily strong. But the Norse vocabulary of joints extended far beyond this single connection. At corners, where two walls met and had to resist the outward pressure of a roof, trying to spread them apart, builders used what we now call the bowl notch, each log receiving a curved cut exactly half its thickness, the two cuts interlocking so precisely that the corner became a single unified mass. No gap, no rotation, no separation possible under lateral load. Where rafters met ridge beams, craftsmen combined 3 separate joint types simultaneously: a seated notch to prevent downward sliding, a lateral shoulder to resist sideways movement, and a tree nail driven through the entire assembly to prevent uplift in high winds. 3 independent mechanical systems, working together, each one catching what the others might miss. This was not over-engineering. In a structure expected to carry several tons of turf and snow across a span of 15 to 20 meters, every connection point was a potential catastrophic failure. The Norse response was redundancy, never trusting a single joint to do what 3 joints could do together. What is perhaps most remarkable is how this knowledge was transmitted. There were no architectural drawings, no written specifications, no formal schools of construction. This entire language, hundreds of joint variations, each with specific applications, specific failure modes, specific tolerances, lived entirely inside the hands and eyes of master builders, passed from father to apprentice, across generations, through demonstration and repetition. To lose one master builder to illness or war was to potentially lose an irreplaceable chapter of this knowledge forever. They did not write their wisdom down. They carved it into the bones of their buildings, and some of those buildings still stand today as the only remaining text. There is a particular quality of cold that people who have never experienced a Scandinavian or North Atlantic winter cannot fully imagine. It is not simply low temperature. It is a cold that is wet and moving, carried by wind that finds every gap in every surface, that pulls heat from a human body faster than metabolism can replace it, that makes the difference between a well-insulated wall and a poorly insulated one a question not of comfort, but of survival through the night. The Viking solution to this specific problem was not technical in the conventional sense. It was geological. In regions where timber was abundant, mainland Scandinavia, parts of Denmark, builders packed additional insulation between double wall constructions, filling cavities with moss, animal hair, or compressed organic material. But in Iceland and Greenland, where the Norse settled from approximately 874 CE onward, usable timber was genuinely scarce. Trees were small, sparse, and insufficient for full wooden wall construction, so they built with the earth itself. Turf, the top layer of soil, bound together by the root systems of grasses and low plants, was cut into blocks and stacked to form walls that could reach 1 meter or more in thickness. Not thin walls with turf facing, solid turf walls with timber framing only as internal structural support. The thermal properties of a wall this thick are genuinely extraordinary. Earth has high thermal mass. It absorbs heat slowly and releases it slowly, meaning the interior temperature of a turf-walled structure stabilizes and resists rapid change in either direction. On a night when external temperatures drop to -20 or -30 Celsius, the interior of a well-maintained turf longhouse could remain survivably warm from body heat and a single central fire alone. But the genius of turf construction went beyond insulation. The root systems within each block did not die when the turf was cut. They continued growing, slowly, persistently, interweaving with the root systems of adjacent blocks. Over months and years, what began as a stack of individual earth segments gradually became a single continuous biological mass. The wall grew stronger as it aged, without any human intervention, driven purely by the quiet persistence of living root systems finding each other in the dark. Archaeological analysis of turf wall remnants at sites including Thingvellir in Iceland suggests some turf constructions achieved structural coherence comparable to mortared stonework within 3 to 5 years of initial construction, not through any deliberate engineering, but through biology, doing what biology does when given time and moisture. The builders did not create the wall's final strength. They simply created the conditions for the wall to strengthen itself. And above all of this, above the turf walls, above the timber frame, above the entire accumulated wisdom of foundation and joint and insulation, sat the roof, the most exposed surface. The one element that faced the full force of every storm, every freeze, every thaw, every year. It needed to be waterproof. It needed to be insulating. It needed to be heavy enough that no wind could lift it, yet light enough that the structure beneath could carry it without collapse. What the Norse built on top of their longhouses solved all 4 problems simultaneously, using 2 materials that cost nothing and existed everywhere. Birch bark. It is one of the most quietly remarkable materials in the natural world, and the Norse knew exactly what they had. Birch bark contains betulin and betulinic acid, natural compounds that make it chemically resistant to water absorption, microbial decay, and fungal growth. Archaeological samples of birch bark recovered from Norse and pre-Norse sites across Scandinavia have been dated to over 500 years old, while retaining measurable flexibility and waterproofing integrity. The builders laid it across the roof decking in overlapping sheets, lower layers covered by upper layers, each overlap precisely calculated so that water moving downward across the surface would always travel over the next sheet rather than under it. In heavy rain, in snowmelt, in the slow, persistent drip of weeks-long Scandinavian autumn, Not a single drop could find its way through. But birch bark alone had one vulnerability: wind. A sheet of bark, however waterproof, is light. A sustained gale across an exposed longhouse ridge could lift it, curl it, tear it free in sections. The Norse solution was characteristically direct. They buried it. 2 layers of turf were laid directly over the birch bark surface. The first layer placed grass side down, creating immediate root contact with the bark beneath, anchoring the biological layer to the waterproofing layer. The second layer placed grass side up, so that within a single growing season, a continuous living carpet of grass and low plants established itself across the entire roof surface. This living roof, once established, weighed several tons across a standard longhouse span. No wind in the North Atlantic was capable of lifting it. And as the root systems of the upper turf layer grew downward through the lower layer and into contact with the birch bark beneath, the entire roof assembly gradually fused into a single biological structural unit, waterproof at its base, thermally massive in its middle, and permanently anchored by the weight and root grip of living vegetation above. The roof did not just cover the house. Over time, it became part of it, indistinguishable from the landscape around it. A green hill that breathed with the seasons, that turned white in winter and green again in spring, that sheltered the people beneath it the way a hillside shelters a valley from prevailing wind. From a distance of 200 meters, a Viking longhouse was invisible. It had become the land itself, and inside that invisible hill, life continued. The central hearth, the Langeld, burned continuously through the winter months, its fire fed by whoever woke first in the darkness before dawn. The smoke it produced had no chimney to escape through, only a gap at the roof ridge, and the slow upward drift of heated air carrying soot and tar compounds into the timber above. This was not a design flaw. It was, in the way that so many Norse solutions were, a problem that solved another problem. The smoke that made eyes water and lungs ache was simultaneously preserving the structural timber of the roof, coating every rafter, every crossbeam, every ridge connection with a thin layer of natural tar compounds that inhibited fungal growth, repelled wood-boring insects, and slowed the absorption of moisture into the grain. Buildings maintained by continuous habitation, kept warm, kept smoky, kept alive with human presence, lasted significantly longer than abandoned structures exposed to the same climate. The house needed the people as much as the people needed the house. Benches ran the length of the walls, serving as seating through the day, sleeping surfaces through the night, storage platforms in the space beneath them. There were no private rooms, no walls between individuals. The entire clan existed within a single shared volume of smoky, firelit air, sleeping within reach of each other's warmth, waking to the same sounds, moving through the same space. This was not poverty. Archaeological evidence from high-status longhouses shows carved decorative elements on interior posts, imported goods stored along walls, evidence of significant textile production and metalworking within the same structure. This was a deliberate social architecture, a physical space designed to produce a particular kind of human community, one where isolation was structurally impossible, where the warmth of the fire was collective property, where survival was, by design, a shared project. And perhaps that, more than any joint, any foundation stone, any birch bark layer, was the most important engineering decision the Norse ever made. We began with a question, not about technique, not about timber joints or stone foundations, or the chemical properties of birch bark. The real question, the one I asked you to hold at the very beginning, was this: what did these people understand about nature that we have forgotten? Here is what 1,000 years of storms taught the Norse builders. Rigidity is fragile. A wall that cannot move will eventually be found by a force large enough to break it. A joint that cannot flex will crack at the point of greatest stress. A roof that fights the wind will, given enough time and enough storms, lose. But a structure that moves with force, that receives pressure and distributes it, that bends without breaking, that yields without collapsing, can outlast almost anything the natural world produces. This principle did not stay inside their buildings. It lived in their ships, which flexed across open ocean rather than resisting the waves. It lived in their social structures, which absorbed newcomers and adapted to new landscapes rather than enforcing rigid hierarchy. It may have lived, in ways we can only speculate about, in how they understood their own lives. In a world where winter was not an interruption of normal existence, but simply another season to be navigated with intelligence and preparation, the Longhouse was not just a shelter. It was a philosophy made physical. The idea that survival belongs not to the strongest, but to those wise enough to know when to bend. Modern architecture operates on almost entirely opposite principles. We build with steel and reinforced concrete, materials chosen specifically for their resistance to deformation. Our structures are designed to be immovable, and when they encounter forces larger than their design tolerances, earthquakes, floods, the slow, patient pressure of climate, they fail suddenly, completely, catastrophically. The Viking longhouse failed gradually, gracefully, warning its inhabitants with creaks and shifts long before any structural compromise became dangerous. It gave people time. Perhaps that is the most human thing about it. We have spent this entire video looking at stone and timber and earth and bark. But what we were really looking at was a community of people who understood something profound, that the world is larger than any structure you can build against it, and that the only architecture worth trusting is one that knows its own limits. The storm is still out there. It always will be. The only question is whether you build something that fights it, or something wise enough to let it pass. What ancient survival technology would you want us to uncover next? The thermal engineering of Native American teepee construction, the permafrost architecture of the Athabascan people, the lost waterproofing techniques of the Pacific Northwest tribes. Leave your answer below, because the most remarkable human knowledge is almost always the knowledge we came closest to losing forever.